Yes. Okay. So a little bit quick thing about me. I have a PhD from Brussels in mathematical physics and a master's from Chalmers in physics. I have a consultancy firm that I founded 4 years ago where we do applied machine learning. I've been working for a couple of, for example, couple of really big customers, as can be seen in the list. And today I'm invited as a founder and organizer of the Gothenburg Artificial Intelligence Alliance or Association. And we have a yearly conference in machine learning, AI, data science, and data engineering. It's non-academic, non-profit, which is a little bit different to many conferences out there, especially in machine learning and AI. So basically about local focus of applied machine learning in Gothenburg. And we do perhaps have Sweden's greatest community of machine learning engineers. I think we're bigger than the similar community in Stockholm, which is good. Myself, I've been working with machine learning for a long time and have maybe like 30 machine learning systems in production over the years. So really seeing the transformation that has been going on since this began. So part one, trends. And one of the big trends that we're seeing in machine learning and AI right now is what I call the engineerization of the machine learning workflow. And with that, so I don't know how much you are aware of how machine learning works, but basically the workflow is that you start with some data, you do model training, you deploy or build that model, you test it, and then you put it in the machine learning system. So that could be, for example, you get your data from a relational database, you have some Python code that is training the model, you have some CI/CD or some system that can build these artifacts, test them and put them somewhere, usually the cloud, and then you have a software system deployed somewhere that is using those models for some business value creating purposes, some prediction. And the example here would be the data would be number of passengers using a specific bus at a specific time. I train a model that tries to predict how many passengers will be on a specific bus on a specific time. I can deploy that model in some cloud environment to run predictions, and the basic model will be used in a mobile application that can tell you how many people will be on the bus that you're about to take, so you can avoid it if you think it will be overcrowded. That's an example of a very simple machine learning workflow. And in the past, this workflow has been very non-engineering in the sense that you have analysts or data scientists that just put something together with some random spaghetti code and have something in production that is not version controlled and not tested and not anything. So, and this has radically changed now. So the machine learning tooling landscape, I would say that the landscape of both closed source and open source software used for machine learning training, experimentation, deployment, and all those things have completely changed in the last 5 years. I would call it a paradigm shift almost. We'll go through a couple of examples for that. And the amount of engineers that work with and understand applied machine learning has probably increased by a factor of 10. I'm said since 2012 here, but it's probably maybe in the last 5 years even. It's been really changed, partly due to the fact that industry is starting to use these cases or seeing machine learning value in production, but also because of universities like Chalmers and KTH have really churned out machine learning engineers in new master programs and so on. But basically, the industry's ability to use machine learning and data science and AI to create value is now down to data, software engineering, use cases, and culture. And we'll come back to that sort of conclusion in the end. But so now we'll take a few open source software examples. Is really what has part of transforming the landscape. So these are fairly technical examples, but I will try to walk them through just to get an idea. And since you're software engineers, you will understand the basics. But basically, so these are two open source softwares from Microsoft that has been released in the last couple of years called Hummingbird, and also an open initiative called Onyx. And Hummingbird is a software that converts standard machine learning models to tensor computations like matrix multiplications and so on that can be run on GPUs. So they're seeing 65 times speed ups from you take a standard machine learning model like what we built 5 or 10 years ago. Now we can convert that into some optimized GPU deployments. So this is really state-of-the-art machine learning software that Microsoft right now has released for the world to use for free, which is transformative in some sense. So you can take a standard decision tree and you convert it to a Onyx format, which is a standardized set of operators, either for CPU, GPU, or FPGA for the hardware people out there. So it's not only cloud, but basically standardized artifacts that run optimized on a specific set of processing architecture. And the Onyx runtimes, which is basically some software that can run these models, it's available on every cloud platform and you can easily deploy it on hardware and so on. So you really get industrialized or engineerized set of techniques that you just put your model in a standardized framework on any kind of architecture or platform that you want. 5 years ago, this would not have been possible, for sure. So another thing that is transformative is something that we call data and model version control. So we all know that code version control is super important in software engineering projects. And in machine learning, we also add the complexity of having to version control the data and to version control the models. And that is also something that was not done before, but now has been made sort of easy with frameworks, open source frameworks. I'm just mentioning one here, which is DVC. It just stands for data version control. So easy. It was released in 2017, version 1 in 2020, and it enables completely reproducible machine learning workflows like the one we saw. And this is sort of how we can make machine learning into a science, so reproducible and engineerized, industrialized. So you have model version control, which means that the model that you deploy to production, you can know exactly what code trained it and what data you use to train that model. So, and you can also, you have the ability to go back in time to previous versions to get the previous code and the previous data and so on. So it's very much like Git or your standardized version controlled software, but for data and the model. It's low cost. It's open source. It doesn't require any fancy cloud architecture. You only need some place to store the data and the models and a Git repository. It's sort of a minimal requirement in every machine learning project, I would say, that you also do data and model version control in order to make it more reproducible, which we want, since this is almost science. Right. Example 3 here on the machine learning frameworks that have proliferated over the years, or the last couple of years, is something that is called Kubeflow. And this is the most advanced example I will bring up here, but it's basically open source. It comes from Google, so it's based on their internal frameworks for handling machine learning. It went to 1.0 in 2020. It's based on Kubernetes, so you would have a Kubernetes cluster, which is of course a hassle. But if you have that, you can do automated training of machine learning models at scale or Google scale, or just your normal standard scale that you want. It's completely up to you in a completely productionalized environment. So you don't train your model on your local computer, but you do it on your cluster. And that means that there is no human in the loop, which decreases the amount of errors. So it's another step of engineerization or industrialization of the machine learning workflow. It has, it's super huge framework, completely open source, Apache license, where you can do experiment management, deployment, collaborations of models, you do testing, you do basically everything. And it's you have managed versions that are available on machine learning or Azure, you have it on AWS, you have it on Google Cloud, you can do it on-prem because everybody can deploy Kubernetes clusters and so on. So it's basically, it's like a Ferrari for machine learning workflows. And it's not for everybody, but it's basically a show that you have, it's transformative in some sense that you have this kind of framework with, you have a lot of big organizations behind using it. Right. So trend number 2 is the standardization of the machine learning model. And what I mean with this is, so here we'll be more machine learning oriented. But so I'll take a little bit slower here. But basically, we start with natural language processing, which is basically the big thing in AI right now. Everybody's doing language processing, and we'll take a couple of examples of that before. But basically, language processing is a sequence problem. I have a sentence, my dog is cute, he likes playing. And I can turn this into what's called autoregressive language modeling problem by trying predicting the next word of these sentences. So I start with, for example, my dog is, and I try to make the model predict the word cute. And then when I have the word cute, I can go on and try to predict the word he. And when I have he, I will try to predict the word is, and so on. So this is a language modeling problem. You can do it in a lot of different ways, but basically this technique is what has transformed language, machine learning, AI over the last couple of years. So, and the way it works is that you turn each word into one or more vectors, and those vectors are fed into your model, and the model is then using those representations of each word to try to predict the next word. And we have an example here of how this looks like in Google's famous BERT model, where we have exactly this sentence that is tokenized, and the token embeddings here that means that we have a vector for each of these input items. So my dog is cute, comma, he likes playing. Then we can have segment embeddings that just tells what part of sentence it is the first part or the second part, and also where in the sentence is the word, and so on. So you turn this into a couple of vectors. And this is basically transforming, this technique of vectorizing the sentence, and then you start putting into a model that is called a transformer. And it's just a fancy word for a lot of matrix multiplications and dot products and so on. But basically it was introduced in 2017 by a couple of guys, Vaswani et al., in a paper called Attention is All You Need, which has, the most famous machine learning papers over the last 5 years, probably. And they completely dominated the NLP sphere. And the most famous example is maybe GPT-3. It has been mentioned in newspapers and so on. It's the model from OpenAI that they claim was so dangerous they wouldn't release it to the public. And now the trend here, the standardization of the machine learning model, is basically that this architecture is slowly moving into what we call modalities. And modalities is different kinds of data. So text would be one modality, image is another, tabular data like financial data, that's one modality, and so on. And now we're also seeing this applied to multimodal data sets, that you have the same model that can handle both image and text, let's say. We'll have a couple of examples of that. The transformer is a very easy to understand architecture. You need to know linear algebra, but if you know some linear algebra, you can basically understand how it works. It's just, you make everything a sequence of vectors and you put it into the architecture and something comes out. It's well tested, and you have accelerated implementations that can be run on GPU and so on. So it can easily be transformed, for example, to this Onyx architecture to be deployed on an FPGA and so on. And I think it's on the next slide. Yeah. So I think what made the rounds in the newspapers a couple of days ago was a Google engineer that claimed that they had a model that had become sentient. I think he probably destroyed his career from that. Hopefully he did. But basically, this is just what he's talking about, just a transformer. It's just that this architecture that was introduced in 2017, it's just matrix multiplications and dot products. It's just a huge amount of them. The models have a lot of parameters that you're training and so on. So it's matrix multiplication in the end, and this transformer architecture. So what is happening right now is basically this is turning into other modalities. You will now have vision transformer, which is the same architecture that people use for language, but you can now apply it to a picture. So you turn the picture into a number of patches, and those patches become a sequence of vectors, and you just input them in the same architecture. So the vision transformer was released in 2020 to handle computer vision problems. It's a single transformer-based networks that almost replicate the performance of what's currently the state of the art in computer vision, CNN-based networks. The image becomes a sequence of flattened image patches, which are 16 by 16 pixels. And just like we did with the sentence, this becomes a sequence of those patches. It's a very active area of research where you have, for example, a lot of different versions of this that tries to solve different computer vision problems. But basically, it's the idea that you have the same architecture that we used for language, but now for pictures. Right. Another transformative idea here, which I think also aligns with a lot of people from Chalmers, for example, is that you have now a decision transformer, which is the same kind of architecture, but can now be applied to reinforcement learning. So reinforcement learning is this problem where you have a machine that tries to, for example, play a game, or maybe a car that tries to drive on the road. I mean, there's a lot of implications of reinforcement learning where you would ask the machine to take some actions to maximize some reward. Let's say, don't drive on the pavement or follow the lanes or something like that. So it's very active research, but what people are doing right now is trying to use the transformer architecture to solve this problem as well. So here you would have something that is called a decision transformer. It was released last year by a collaboration of Google Brain, Berkeley, and Facebook AI. And it basically tries to solve a problem that is called offline reinforcement learning as a sequence modeling problem using transformers. So you take if I'm playing a game, I want to solve the level by jumping up and down and avoiding the enemies and so on. And this is a sequence of actions that I take, and the state, sort of where are my enemies, and then some reward is that I should not be killed. Let's say I should increase the amount of money or points that I get or something like that. And you can just make a sequence of that where you have a state, action, and reward. And you input that sequence, you vectorize that sequence, and you put it into the transformer. So basically, you turn that reinforcement learning problem into exactly the same kind of vectorized problem that we did with the language. And it's just, the idea here is that, we have the same model, we just transform the data in different ways. So the third example here is something called Gato. It was released by DeepMind, it should be, May this year, and it also made the newspapers. It's there. I mean, in some tech newspapers, they basically said that this is also a way of human level, next step into human level AI, but it's nothing magical here happening either. It's basically it's a transformer architecture, but what they have done now is that they have made it multimodal. So you basically feed it all the different kinds of data. So you can feed it images, you can feed it text, you can play it Atari game sequences and so on. And you vectorize all these things, and you get this sequence of vectors as well. So it can put captions on an image, play Atari games, do question and answering, all with the same architecture, the single model. Get these vectorized sequences. And one of the big things about this one is that it's relatively small. I know that this is huge for most of us. It would be huge for me, but for DeepMind, this is a small model. It only has 8 billion parameters, and that can be compared to GPT-3 or the Lambda model that we talked about before, this sentient model, which has hundreds of billions, I mean, more than 100 billion parameters. So hopefully the same weights in the network knows both about images and text. This model, the only magical thing about this model is a little bit the tricks they use to make all these different modalities into the same kind of sequence, so they can train it simultaneously. And it's also made possible by DeepMind's unique connection of data sets and, of course, Google's training infrastructure. To develop these models costs millions of dollars. And this made the news because it can play, the same model plays games and answer questions and so on. And you can think of, okay, a human can do that as well. But basically, it's about tokenizing the data sets and training it with the transformer.
Josef, I have a lot of questions, but can I ask one question now?
Yeah, sure.
So in those multimodal models, do they link those multimodalities in such a way that there is a one weight or one vector that is similar for, you know, a picture of a tower and the word tower somewhere, or the voice tower, or they are just
no, those connections will have to be made internally in the network.
Okay.
Yeah.
Okay.
So basically, the word tower is tokenized or vectorized to a specific vector, and then let's say the image patch that contained that tower will be vectorized to some other vector that will be fed. But then hopefully the network learns to recognize that these are just different representations of the same thing. So maybe at a couple of layers deeper into the network, they will maybe be represented by the same thing.
Okay, but there is no explicit link.
No.
Okay.
Okay,
Good.
no. But that's the big question of this network is basically, is it actually realizing that, or is it just a couple of different copies of this? Would you have a computer vision model somewhere in the layers of that model and a separate model handling the text, or is it actually, are they sharing the weights? I think that's
there is no answer.
Well, I don't know if we know yet.
Yeah.
Okay, but the assumption is that it actually is, and that's why they made the model smaller to force it. Because a huge model, then you would have a lot of.
Yeah. Okay. Sorry for disturbing.
No, yeah, it's a good question. So the next now we come for implications.
You don't have to stress. We have the entire.
All right.
Okay. Right.
Okay. Yeah, I'm almost talking too fast. Okay, but basically, so historically, the task of the machine learning engineer has been to first find the right model framework for the data set at hand. So basically, you start with a problem. Let's say I'm trying to predict the number of people on a bus. Now I need to find, okay, what model should I use? And basically, that model should, to increase the performance of that model, we do something that is called inductive bias. And inductive bias is that we insert something about the problem into the model. So we tell, we know that it's a problem about predicting passengers. Okay, maybe the model knows something about that kind of problem. And it's a computer vision. You have these convolutional neural networks, which is very much inductive bias to how we treat pictures, let's say. We also introduce inductive bias, which is just a fancy name for domain expertise, into the problem by doing something that is called feature engineering. So when people did computer vision before neural networks, basically computer vision was a lot about feature engineering, that you took the picture and you tried to transform it into some different representations, like the number of black pixels, or I know, stuff like that. So these is ways of, inserting something about what you know about the problem into the network. And for highly specialized problems, maybe the engineer even need to develop their own architecture from scratch, because there is no model that has enough inductive bias for the specific problem at hand for you to be able to get the performance that you need, basically. So that was usually the workflow of people back in the day. But the trends that we're seeing right now is basically this is now changing to becoming all about the data. And transformers is basically a big part of that. So if you have the same architecture, which would be the transformer architecture, you get rid of both the feature engineering and the model engineering. So basically, we don't need to input any inductive bias into the model. We don't need to find a specific model. We don't need to do feature engineering. We don't need to do all these things. We can just use the same architecture for all the problems. So the task of the engineer will be basically to engineer the data and then engineering the final machine learning system. So you write the code for processing the data to turn that into the vectorized sequence, and then you write the code to put that into production, like handling the data in production environment and stuff like that. So what remains basically of the machine learning workflow of the training and processing and so on is just the pre-processing of turning your specific data into the vectorized sequence that you input into the transformer. And I'm calling this data set engineering. There's a lot of different words from here. This is happening right now, so we don't have really a word for what's happening, but I call it data set engineering. So what does this imply for the software engineer and the machine learning engineer? And I know that people, Software Center, you're very much interested in testing. Testing is a huge part of software engineering and software development. So, what happens now when we have these trends? First of all, that the standardization of the machine learning model is that the model architecture is fixed and well established. It means it does not have to be tested. You can basically take it for granted because it has been tested all over the place by millions of people. You know that it's working. The ML engineer solving a specific problem can take the quality of the model for granted in most cases. So here I'm simplifying a little bit, but basically it means that the testing of the machine learning workflow is instead only needed for the data set pre-processing, which is a completely deterministic problem. I just want to see if I have data looking that way and I transform it, it should look this way. So this I can solve with just deterministic unit testing, or the way that we always handle functional testing in software engineering. The machine learning system, of course, need to be tested in the standardized techniques like from software engineering, such as integration testing, regression testing, and QA, and so on. But this has this is nothing machine learning specific. There's no statistics in here. There's no stochasticity. There's nothing magical. It's just standard software engineering testing. And with all these frameworks, like with Kubeflow that I mentioned, this Google scale machine learning in production kind of environment, you also have the system to automate and replicate all these things in a standardized way that is also don't need to test, but you can automate it and you can run these unit tests that you pre-process with and so on in sort of like industrialized or standardized frameworks. Right, so I'm running it on time and we can have the discussion anyway. So the conclusion would be that, okay, machine learning has always been on the border of software engineering, and there's always been a discussion of how much is machine learning software engineering and how much is AI magic things that only machine learning engineers can do, and how much is statistics and so on. But if we're taking these two trends, basically the engineerization of the machine learning framework and the standardization of the machine learning model, you basically get down to the situation where you have only a handful standardized and established model architectures that can be used for most current industrialized machine learning problems. The prominent training, testing, and monitoring of these models can now be done with standardized, easy-to-use, and established open-source frameworks. Understanding of these models and data sets still requires statistics. So you never get away from the statistics part. You always need to understand what you're doing, and the more complicated the problem is, the more statistics you will need to know in order to understand the predictions. But there is sort of biases or sample selection bias, stuff like that statistics handle that you'd never get away from. But basically, the standardization and engineerization of the other parts turn everything else into standard software engineering. That's my claim. And it might be a little bit provocative, but I think it's actually true. So this is something that also some people call data-centric AI, that the work of the machine learning engineer or the artificial intelligence researcher becomes working with the data, because the model and the infrastructure and architecture, that's already fixed now, basically. So, yeah, this was my attempt to turn the problem of what's happening in AI into a discussion about software engineering and also about machine learning in production.